Hello everyone and welcome to PrepFusion. This is the lecture 6 of the basics of control system. So before starting this lecture, right, I have given you homework of this question. We'll solve this question first, and also we'll learn few more topics, the last few topics, right. But before that, I will give you quick recap of what we did in the fifth lecture, right. So in the fifth lecture, we learned about pole zeros, the concept of time constant, and the effect of feedback, right? The effect of positive feedback and negative feedback. So firstly, we learned what are pole zeros. Basically, pole zeros are like poles are roots of this denominator and zeros are roots of the numerator, right? Then we found out poles and zeros, how to find them out. Okay, all these things I hope you understand. Like we found out like what is sigma plus j omega plane. Like S has two components. One is real component and one is the imaginary component. So the real component, right, will lie on this axis and imaginary component will lie on this axis. So like we found for complex conjugate roots, we found for real roots, and what does poles represent, that we understand, right. All this can be said for time constant also. The pole and time constant are just inverse of each other, like for that case. So here, like we proved in the later stages of the lecture, right, that how does time constant represent time response, how does time constant represent performance, speed, stability, all these things, right. Okay, all these things. So poles also represent the frequency of oscillation. Okay, just by finding the imaginary component, right. If there is complex conjugate root, this imaginary component will be the frequency of oscillation, right. So yeah, that is basically the poles definition. Now for a stable system, the pole should lie on the left half of the S plane or the left half of the j omega axis. Okay, so we took few examples and we like proved that yeah, it should lie on the left half of the S plane. Even if repeated poles lie on the imaginary axis, the system will be unstable. If complex conjugate poles lie on the imaginary axis, the system will be marginally stable. Marginally stable means the system will oscillate between certain range of values. Okay, it won't go unbounded or it won't settle to some value. It will keep on oscillating. Okay, so yeah, for marginally stable, like we did when there is a frequency of oscillation in a signal, right, then the signal may be stable, unstable, or marginally stable depending upon the real component. Where is that real component of the pole present, right. So yeah, all those things we did. Then we like taught you how to realize poles and zeros intuitively, right, without like directly writing the equations and all those things, okay, in Laplace domain. But for that, like if you didn't understand, that's okay, you can watch the video of mine or Himanshu, any video where that is available on YouTube. But this is not that important in control system, but just in case it may come in handy in some some stage, right. So that's why I told you. Okay, so this don't need to take too much pressure on this. Now we learned what is a time constant, like what are time constant defined as. There is one basic definition of time constant, is that the time for which it reaches its 63.2% of its final value, right. Reaches to 63.2% of its final value, but that is for only for the definition for the first order system. For other like higher order systems, the definition won't be valid anymore. So this definition is always valid, that time constant is defined as reciprocal of magnitude of negative real roots for a stable system. Okay, so yeah, this is one thing. So we did that. If we have a given transformation, how to find the time constant, all these things we did. Okay, so again, for unstable system, time constant doesn't exist. Okay, time constant only exists for stable systems. Okay, so then we wrote the general time constant form of a control system. So this is the general time constant form. All these things are just basics only. Here this is very important, that the time, like settling time and the speed are inversely reciprocal to each other, right. That's why speed is related to time constant as inverse relation. Okay, so yeah, we compared three graphs, okay, whose speed is higher and whose time constant is lower. Okay, all these things we compared. Then we went to the effect of feedback. What happens to a system, open system, if I give it a negative feedback and if I give it a positive feedback. Okay, if I give it a negative feedback, what will happen? The pole will shift more towards left, hence the system will become more stable and the time constant will reduce further, hence the speed will increase. The speed of the system will increase, the performance will increase. Okay, so all these things will happen in when we use negative feedback, right. So yeah, this was the negative feedback response. Initially it was wrong. Okay, this was the negative feedback response. Okay, so like if impulse is given, this is the transfer function, right. this stable system only, and the speed has increased here right now. So like if for example if we give us, we would have given a sinusoidal signal, then this would have been the response. Okay, we see energy degeneration, like it is settling to zero, right? It is settling to zero due to this envelope, right? Due to this envelope. Okay, I don't need to worry about like how are you getting x of t and all this. It's just this is just a graph. Okay, just to show you that yeah, we are getting energy degeneration. Okay, so now system with positive feedback, system with positive feedback. So if I give it a positive feedback, what will happen? The pole will try to shift more towards the right. Okay, so if the pole shifts more towards the right and somehow it reaches the right side of the geometric axis, then the system will become unstable. The stable system will become unstable. Okay, so it reduces the stability of the system. Pole shifts to the right hand side of the x-plane. Okay, yeah, that's is the time response of this. Initially x of t was different, now it become unstable, unbounded, right? So yeah, and energy regeneration happens. It gives more energy to the output, right? It gives more energy to the output instead of taking more energy. It gives more energy. Okay, so yeah, that was like the positive feedback. Now initial value theorem, basically it is used to determine the initial value of the time response of the signal in Laplace domain with the help of Laplace domain without directly calculating the Laplace inverse. This will directly give us the information about the initial value. Okay, so x of t is Laplace of x of s. Now limit as t tends to 0 plus x of t equals to x of 0 plus, right, equals to limit s tending to infinity. Okay, so this is basically the formula for this, so you should mark this. This is important. Then we did few example problems of this initial problem. Then I given a few points. If order and like order of this is more, but the order and denominator numerator of this one, right, this equation, not the normal g of s equation, of this s times g of s. Okay, don't get confused. So yeah, now like we did a few problems. Initial value theorem does work for the stable and unstable system. Okay, both. Okay, no worries. And for marginally stable system also, initial value theorem works for all three, because we are only calculating the initial value, we are not calculating the final value. Okay, so initially there may be some constant value, right? So yeah, that is the thing, because for a unstable system also initially there is some value, then it goes to unbounded. Okay, so yeah, that is the reason. So yeah, these are well main points. Then final value theorem we came. Okay, I give you the definition of final value. Okay, how to find the final value with the help of Laplace domain, and we did a few like questions. Here the system is unstable, so there is no final value, it is unbounded, right? So it is not zero. Okay, not zero. So again, if it is marginally stable, again it is not zero. Okay, so final value theorem is only valid for a absolutely stable system. Okay, it is only valid for absolutely stable system. Final value theorem is not valid for a unstable or marginally stable system. Final value theorem is not valid for a unstable or a marginally stable system. Okay, this is a very important point to note. Then this was the question that we will solve this. Okay, so like what is this question telling us is, consider a transfer function with a given s plane and a DC gain of 100. So the s plane is given. In s plane what is given? The poles are given, right? We don't have any zeros. I don't see any zeros, so we have only poles, and the DC gain of the transfer function is given, right? We have to find the roots of the characteristics equation. So roots of the characteristics equation means the denominator, right? Roots of the denominator, basically it is telling us to find. Okay, is asking us to find frequency of oscillation. We need to find. Okay, from the roots we can find that initial value of the transfer function. Okay, again use that initial value theorem. Final value of the transfer function, use final value theorem. Then time domain expression of the transfer function, we do the Laplace inverse. Okay, so first what I see is this has two roots, right? Two roots. So roots of the characteristics equation will be 4 and minus 4 and minus 1. So let me take this. Okay, so we have two roots, right? One is s1 equals to minus 4, another is s2 equals to minus 1. Okay, so like what are the factors here? So I hope you know how to do factors from root side. Factors s plus 4 and s plus 1, right? So yeah, these are the factors. Now let me write the Laplace expression, right? Laplace domain expression. So we can write the Laplace domain expression like this: x of s equals to k divided by s plus 4 s plus 1. Okay, s plus 4 divided by s plus 1. So now what is the DC gain? DC gain equals to k, is it? No, DC gain and k are both different things. Okay, DC gain is given DC gain is given as 100, and k is just a constant. K is just a constant, it is not the DC gain. Okay, here k is just a constant. K is just a constant, there is no relation with DC gain. Okay, there is no relation with DC gain for this. Okay, so yeah, now let's write the DC gain for this. So DC gain is what? The value of the transfer function at s equals to 0, right? Zero frequency gain basically. So this is a type 0 system, so that will be only the definition. So DC gain putting s equals to 0, we get here is 0 plus 4 times 0 plus 1. So this is k by 4, which is equals to 100 only. So k equals to 400. So divided by s plus 4 times s plus 1, right? S plus 4 divided by s plus 1. Okay, so now like what should we do is, like this is the expression for x of s. Now we have to find the like the frequency of oscillation, right? So we are saying the roots are real, right? The roots are only real, there is no imaginary component present, so frequency of oscillation for this will be 0. Okay. Another thing to note here is that what we could have done is, like if you would have written this form, right? Instead of writing like this form, what we could have written is the standard time constant form, right? If I would have written here this, right, a by s tau 1 plus 1 s tau 2 plus 1, then this is the DC gain, right? Then this a, right, this a is a DC gain, this a is a DC gain. How? We put s equals to 0, we are only left with a, right? So then this is DC gain, but we have to write this then in terms of time constant. So what is tau 1? Tau 1 is this inverse of this 1 by 4, so this will be s by 4 and this will be s only. Okay, so here we will get the DC gain, right? This a will be DC gain. Here we can put 100 here, 100 here. Then what we will do, simply multiply by 4 on both sides, then the upper side will be 400, 100, right? Yeah, upper side will be 400, and in the bottom we will get s plus 4 and s plus 1. Okay, so yeah, we will get back this equation only. So you can either write in terms of this, in terms of this also. So any ways you are right. If you write in terms of this, then this a will directly, you can directly write here 100, because you know the DC gain directly in this expression. In this expression you have to find the value of k. Okay, by using that DC gain. Okay, any one of these two you can do. Not present here, no complex conjugate roots are present. Okay, so this this will not oscillate too. This will not oscillate. Now like the third question asks us is to find the initial value, right? So what is the initial value? Initial value, again we'll use the initial value theorem. X of t equals to 0 plus equals to x of s. So like what is this? Basically x of 400 s by s plus 4 divided by s plus 1. Okay, so like what is this value? If I put 0 over here, what I get? Upper side 0. Sorry, if I put infinity over here, like this, the order of denominator is higher than the numerator, so this will only go to 0 only, right? This only go to 0. This will only go to 0. Okay, so now what we can write here is like what is the final value? Final value x of infinity is limit s tending to 0 s x of s. So what is this equals to? Simply 400 s, this will be only equal to 0 only. Okay, so this is starting from 0 and ending to 0, so we don't have any useful information. Equals to 0 only. Okay, so what you have to do is find the time domain expression, right? Find the time domain expression. So what we are given in the Laplace domain is 400 divided by s plus 4 into s plus 1. What we can do is simply use partial fractions, right? So for this pole, right, put s equals to minus 4. This is minus 3 only. S equals to minus 4, so this is minus 3 only. So this will come out to be minus 400 by 3 into s plus 1. And what will this come out to be? Put s equals to minus 1 this time. So if I put s equals to minus 1, I get 400 by 3 into s plus 1. S plus 1. So if I do the Laplace inverse, right, what do I get? I get 400 by 3 e raised to power minus t. Ut I will write at the end. Okay, e raised to power minus 40 e of t. Okay, this is the expression that we get, right? So one more thing to note here is that just we'll learn this in the next concept only, that this term, right, this term will not affect this term. This term will affect it initially, but after that it won't affect. Okay, it will die down, the response will die down, right? So how will the graph look like? So the graph, right, sorry for the introduction, actually call came. So the graph, right, graph will look like a bell shaped, right, will look like a bell shaped curve. This is x of t, this is t, and it will go like here. Okay, so it goes up first, then it goes down. Okay, because at some point, like this response will be more dominated before this. This we will understand in the next few slides only. Okay, so what is happening? The slope, the values are increasing, then it is decreasing suddenly. Let's say this is some value t naught, right? Or let's say this is t dash and this is c, right? So what is the value of c? What is the value of x for which this value changes, right? So from here the slope is reducing, going to 0, and then the slope is negative. Okay, so c equals to x of t dash, and what will be that value? Dx of t dt at t equals to t dash should be equals to 0, right? Slope should be 0. Slope should be 0. Okay, so yeah, this is basically the that thing. So now what we need to do is basically find that this slope, right? So what I will do is simply differentiate this equation. So differentiate x of t. So 400 by 3 anyways stayed outside. We get minus e raised to power minus t and plus 4 e raised to power minus 40 equals to 0, right? Equals to 0. U of t I am not considering because after t equals to 0 plus, right, where the u of t equals to 1 only, it is constant only, so I am not considering that UV rule here. Okay, so this e raised to power minus 3t equals to 1 by 4, right? So this goes there, okay, and this goes in, yeah, is to, or you can say e raised to power 3t equals to 4, whatever you wish to find. Okay, so this is t dash, right? So this is t dash actually, t dash. Okay, again I did it wrong. This is not t1, t dash only, t dash and t dash and t dash. Okay, and t dash. Okay, so yeah, now like what is the value of t dash? T dash is 1 by 3 ln 4. T dash is 1 by 3 ln 4. So x of t equals to, like this is the value of t dash for which we will get that constant. You put this t dash there and you'll get it answer. Okay, now what I want to know is, if x of t is something like this, e raised to power minus t upon tau, or something like this, e raised to power minus t upon tau 1 minus e raised to power minus t upon tau 2, then for both of this, right, the like plot will look something like this, like a bell shaped plot. That is the initial value equals to 0 and the final value equals to 0. Okay, both of them are 0. Okay, so yeah, this was this question. This took a bit of more time than I expected. So let's do the lecture 6 now. So it will be over by quickly only. We'll do this bit quickly. Okay, first we'll learn about the dominant pole method, and like impulse and step response we have already learned a bit of it in Laplace, but here I will explain to you a bit in a more broader amount, right? More thorough, and we'll do questions. Obviously questions I may give you homework also, it depends. Okay, now first we'll do the concept of dominant pole method. So first let me take an example. Okay, transfer function, let me take x of s equals to 120. Okay, now we have two poles, right? So one is at s equals to minus 2, another is s equals to minus 12. Okay, so let me draw the pole 0 diagram, s plane. Okay, okay, so what is this? This is minus 2 and this is minus 2. Okay, so this is minus 2 and this is minus 2. Okay, so this is sigma and g omega. Now let me take the inverse Laplace of this, right? Let me explain it to you what we will do next, right? Why are we doing it? Okay, so x of t, right, what will x of t become? So putting here s equals to minus 2, what do you get is 120 divided by 10, which is 12 only. So 12, it will be 12 e raised to power minus 2t. I am doing this directly now, you have to be like that only. Now put s equals to minus 12, this becomes minus 10. So 120 by minus 10 is minus 12 only, so this becomes minus here e raised to power minus 12t u of t. Okay, so this is our time domain expression. Okay, now what I can do is, if you evaluate this, right, if you evaluate this, let's say I will evaluate this at t equals to 1. Okay, t equals to 1. So this is the, let's say this is this is the y1 and this is the y2. Okay, so y1 equals to like t equals to 1, it is e raised to power minus 2. Okay, and y2 equals to e raised to power minus 12. Okay, so both of them, you see, what do you notice here? This is e raised to power minus 12, which is very small, very small, right? In compared to this, it's anyways very small, right? So we can ignore this term. Okay, so it reaches its steady state much faster. Why? What is the time constant? The time constant of this one, right, is 1 by 12. Time constant is very lesser than this. This is 1 by 2 only. So it reaches its steady state much faster, and the speed of this y2 is very high than this y1. Okay, so it will not contribute much to the time response of the overall signal. Okay, so overall signal, right, so it will not contribute that much. So what we can do is, we can ignore this term, we can ignore this insignificant term, we can ignore yt. Okay, so I'm drawing this now, plotting this here. Also you will better understand visually, right? So x1 of t equals to e raised to power minus 2t e of t, and this is, of course, this is 12, right? Okay, I wrote this as y1 of t actually. Okay, let me ignore the minus sign for now. I'm just I just want to know the magnitude. Care only about the magnitude right now. Okay, so this is y1 of t, this is y2 of t. Okay, so what is this? So basically we're starting from 12 and we're going to 0. Okay, and we're starting from 12 and we're going to 0, but at a much faster rate this time. Okay, much faster rate. Okay, so we reach 0 at a much faster rate. Okay, so like what will happen? This is 12 only. This is, let's say this is 4 tau 2 and this is 4 tau 1. So you can see that it reaches steady state much later. So this signal, right, dies down much faster. Okay, dies down much faster. So like we can write the time constant also, as I explained you, but let me write it also. 1 by 2 and tau 2 is 1 by 12. So tau 2 is much less than tau 1, right? So speed of 2 will be much greater than speed of 1. Okay, so this is basically the concept of here we will use the concept of dominant pole only when one time constant is much less than the other time constant. So here, right, the significant pole is referred to as dominant pole, the pole which is more nearer to the origin. Okay, Why? We'll understand. The time constant, as we go more further from the origin, right, the time constant reduces it because it is inverse of the pole. So significant pole is referred to as dominant pole, and dominant pole exists near to the origin in the left hand side of the spin. Dominant pole exists near to the origin in the left hand side of the spin. For the existence of dominant pole, okay, this has become pole axis, so I have to do this, right, pole here. For existence of dominant pole concept, the ratio of insignificant over significant pole should be greater than 4, equal to 4. So what does this mean? Basically, this means that insignificant pole over significant pole should be greater than equals to 4. That is basically the ratio of the time constant. Also you can say that the ratio should be at least greater than equal to 4, then only we can ignore, right? If their speeds are much nearer to each other, if they are much closer to each other, okay, then obviously we can't ignore the response of one of the signals, right? We can't, okay, then we have to consider both of the signals. But if they are, the one speed is very high and other speed is slow, then obviously we can ignore one of the speeds, right? That is what it is mentioning. And this 4, right, this 4, you don't need to worry how did this 4 came, just you need to remember this, that the ratio of the two poles, right, the insignificant pole that is further away from the origin, the ratio of that and the significant pole that is more towards the origin should be equals to 4 only, okay. So yeah, this is one thing to remember in dominant pole concept. Like okay, this is okay, like I didn't check the spellings here, okay, he wrote it and I didn't check the spelling, sorry. Like the time response due to significant pole is slower than the insignificant pole, that I like already mentioned, right? And dominant pole concept, we neglect the insignificant pole of the transformation, okay, the pole that is more further away from the origin, okay, that we neglect. Concept of dominant pole, like one thing you have to keep in mind is that the transfer function should remain same, right? I mean the values of the transfer function should remain same. By that, what do you mean? That after applying the approximation, as we are ignoring that pole, right, but the DC gain before applying the approximation and after applying the approximation, both of them should remain same, okay. This is one important point to note, okay. Like now we'll learn how to apply the approximation, right? So how to apply dominant pole concept. So basically, right, this x of s, right, what we have got is x of s equals to 120 divided by s plus 2 into s plus 12, okay. So how can we approximate? We will ignore this pole, right, that is further away from the origin. So what I can write here is 120 divided by s plus 2. No, I can't write this. Why? Because the DC gain of this one and DC gain of this one isn't same, okay. So like this is the insignificant pole and this is the significant pole, okay. What is the DC gain of this? DC gain equals to 5 only. DC gain equals to 5 only, okay. But what is the DC gain of this one? It is 60, right? Put s equals to 0 here, you will get 60. Put s equals to 0 here, you will get 5, right? 2 into 12, 120 divided by 2 is 10, 10 by 2 is 5. So we have to make the DC gain same after approximation. So what I will do is simply write here is that x dash of s equals to k by s plus 2, and the DC gain for this, right, should be same. So DC gain equals to 5. So we do k 0 plus 2 should be equals to 5. So k should be equals to 10, okay. K should be equals to 10 only. So x dash of s equals to 10 divided by s plus 2. Now this is the correct dominant pole approximation, okay. approximation. Okay, so this thing you have to keep in mind, or what you can do is write that general time constant format, right? If I write this in terms of time constant format, okay, let me use another pen. Yeah, this one. So 120, I take 2 and 12 common here, so I get here in the numerator as 5, and this has s divided by 2 plus 1 and s divided by 12 plus 1. Now what I do is like ignore this one, right? Ignore this one. Now I will get simply I can write here is that, okay, let me take a different color. This will remain 5 only, and this is because this, right? Now this is the DC gain only, this won't change, okay, and this also won't change. So you can write in terms of this one only, we can approximate, right? Now this won't change, okay. You can write in terms of this one only, or you can do like this one only, that you write in terms of this, then you do this, find the value of k. K is not a DC gain, but this is the DC gain. 5 is a DC gain, and it won't change right now because this is 1, right? And if I make a 0, then we're only left with 1, okay. So yeah, this is the basically dominant pole concept. So let us now like approximate this function with the help of dominant pole concept, right? So firstly we will draw the pole 0 diagram. From there we will understand whether we can apply the dominant pole concept or not, okay. So draw the pole 0 diagram. Okay, so this is j omega. So like this is what, like now what are the poles and zeros. So first one pole I can see is at real axis, sigma axis, at s equals to -10. So this is at -10, okay. And another pole what I see is these are complex conjugate, right? So like what is the equation of this? So if I find the poles for this, right, to find the roots for this, right, so again minus b plus minus b square minus 4ac over 2. These are the poles, right? These are the poles. So what do we get? This is under root -4 minus j2 plus minus j2 divided by 2, so -1 plus minus j1. So two poles lie here, j and minus j, okay, -1, okay. So yeah, this is the pole 0, okay. This is the pole 0. So like here what we see is we have to compare the real part, right? Real part of the pole. Okay, here I missed one part, that we have to compare the ratio of the real part. Real part. Okay, this is very important. So just wait, real part of, so what I can write here is basically the real part, it is -1 and this is -10. So if I compare the ratios of, because time constant is for the real part only, right? Time constant is only for the real part, so from there we can only understand the speed, right? That's why we are comparing only the real parts. So ISP upon SP equals to 10 by 1, okay. So 10. So dominant pole concept, we can apply dominant pole concept, right? So what is this x dash of s? So x dash of s, right, it will become k upon s square plus 2s plus 2, and DC gain, right? What is the DC gain? DC gain, I put s equals to 0 here, so we get 2 times 10 by 100, so 10 by 2 is 5. 10 by 2 is 5 only. So from there we can find the value of k. So x dash of 0 should be equals to 5 equals to k divided by this is 2, so k will become 10 only, right? So our x dash of s after approximation, right, it will become simply 10 divided by s square plus 2s plus 2. Okay, so this is what it will become. So this was basically the dominant pole concept. Now we'll come to another concept, that is the concept of impulse response and step response. I've already given you a basic glimpse of this and we have already studied this, but still I will revise you this. This is valid for obviously only for LTI systems. So for LTI systems, right, we give one input in the system and get one output, right? Get one output. Okay, this is the system. Now how is the input or the excitation and the response are related, right? And the output. Okay, all these things. This is YFT. Okay, so how are they related for a LTI system? For a LTI system, right? So for LTI system they related like x of t is convolution of h of t. H of t is the transfer function of this or the impulse response of this. H of t is defined as the impulse response. Already we have studied this. So if I take the Laplace domain, so convolution becomes multiplication x of s times if I write again cross write you will get confused, so x of s times h of s, and h of s is known as the transfer function, right? We've already done this, all this transfer function. X of s, right? So now what do you mean by impulse response? The response of the system to unit impulse input. And what do you mean by step response? Impulse response I have already taught you. I will just write the step response. Okay, step response response of the system due to unit step input, right? Due to unit step input. Okay, so now what will happen? Now like if I want to find the impulse response, like if I do convolution of with del of t, right here, del of t, if input is, sorry, if I do convolution with del of t, if input is del of t, then the convolution of del of t with h of t becomes h of t only. It becomes h of t. Or here if the Laplace transform of del of t is 1, so it becomes h of s only. So we have already done this. Okay, I will write this in very fast manner. Okay, that I'll just write the step response, because impulse response I have already taught you. So I will just write the step response. Impulse response is the transfer function. All those things I have already taught you, right? So this is h of t only. Still I will actually do that. Okay, so let me then take another page actually, because it may so happen you may miss some notes. Okay, so we have this h of t, right? Now we have this x of t and we have this y of t. Y of t equals to x of t convolution with h of t, right? So now if x of t equals to del of t, so del of t convolution with h of t, it becomes h of t only. So the response becomes h of t. That is the like the impulse response name suggests, right? If I take the Laplace inverse here, so y of s becomes h of s only. Okay, so impulse response is basically the Laplace inverse of the transfer function, you can say. Okay, This is already I have taught you, but still. Okay, now or we can say the Laplace of impulse response, right? It is the transfer function. Okay, it is the transfer function. So this is basically it for the impulse response. Now I will do it for the step response. Again the similar thing. Okay, I will just copy and paste this. Okay, change few things because we are constrained with time. So make this a bit smaller. This time what we are giving as input here, we're not giving del of t. What we are giving is u of t, right? And this changes to u of t. So if I do a step response, right, what happens is we are simply integrating the signal. So here we are simply integrating the impulse response. Okay, or if I do this, right, if I take the Laplace inverse, then y of s becomes h of s will remain. Okay, h of s will remain, but times a 1 by s. Why? This becomes multiplication in Laplace domain. This is h of s and this becomes 1 by s, right? That's why this 1 by s comes. Okay, the impulse response, right? Okay, let me write the step response here. The step response, let me write in smaller pens. Step response will be simply 1 by s times the impulse response in Laplace domain, or we can simply integrate it, right? We can simply integrate it 0 to t the impulse response dt, right? Or whatever term you want to say, or what I can write is the impulse response, right? I can do the opposite effect, right? Impulse response will be differentiation of the step response for the same same system, right? For the same system. So let me copy this, let me bring it back to that side actually. Okay, so also one more thing, if you do this, right, differentiate this, then generally what happens, we ignore the unit step function, right? In multiplication we have a u of t, so you have to, whenever we're differentiating, right, we have to take care of the product rule, right? U times v, differentiation of u times v. So just keep in mind when we will solve this, I will explain you what do I mean by that. Okay, so just keep in mind this is sometimes a bit risky. Okay, now we will solve a question. Okay, we have a question, right? So we have to find the impulse response of a system e raised to power minus 2t ut. Okay, find the step response, that is impulse response of a system is given, right? We have to find the step response, and also the step response of a system is given, the same signal only. We have to find the impulse response, so we have to find two things. Okay, for one case impulse response is given, so if impulse response is given, simple, we will just integrate the impulse response and we will find the step response. So we can solve this using multiple methods. So let me first solve this for the one, right? Method 1. So what we are given is h of t equals to simply e raised to power minus 2t u of t. This is the impulse response, right? What I will do to find the step response, I will just simply integrate, right? So 0 to t e raised to power minus 2t u of t dt. So what do I get? It is simply changing the variables, right? What I need to do is changes to tau actually, else you will get confused. Doesn't matter, right? Just changing the dummy variable. okay, tau. Now between 0, this u of t is 1 only, so this u of t will, we can change this to 1 only, right? Now integrate this, so what do I get? So I get minus 1 by 2, then e raised to power minus 2 tau, put 0 and t, okay. So what do I get is 1 minus e raised to power minus 2t divided by 2, okay. So this is basically the solution that we get, and u of t is also there, okay, because before t equals 0, this is 0 only, so I will put u of t, okay. So this is the step response y of t, okay. Now what is the second method? What you can do, use the transfer function method. Find the transfer function and then solve it in Laplace domain, and then take the Laplace inverse of y of s and find the value, right? So this was method 1, transfer function. H of s equals to, simply we are giving some x of t and we are taking some output y of t. So x of t is u of t only, so if I take the Laplace of this, okay, I get 1 over s, and like we are given here, like I should write, okay, I went to some other page. If we are given here h of t equals to e raised to power minus 2t, right? I don't have enough space, let me just into u of t. So what do we get? We get here is, if I do the Laplace transform of this, right, is 1 by s plus 2. If I do the Laplace transform, I get 1 by s plus 2. So what will be the Laplace transform of this one? What will be y of s equals to, simply this x of s times h of s. So this is equals to 1 by s by 1 by s plus 2, okay. Now what I will do, simply do the partial fraction again. So y of s equals to 1 by s, putting s equals to 0, I get 1 by 2, okay. So 1 by 2 will be outside, this will be 1 by s, and putting s equals to minus 2, I get minus 1 by 2, right, minus 1 by 2. So minus 1 by s plus 2, so this is 1 by 2 e raised to power, this is 1 only, right, unit step, minus e raised to power minus 2t into e of t, okay. This is our y of t, okay. So yeah, this is our step response, right? Okay, this I took the Laplace inverse, I skipped a step here, took the Laplace inverse, okay. I have your understanding now. For like these should be on your fingertips, you should do very very fast right now, because like I hope you have practiced of this enough, right? So now we'll solve the second question, right? Second question. So okay, let me write this as, like, this is 25, let me write this as 25, this one 26, right? This one 26, right? So this is actually 25, okay. So now let me solve this. 26, right? Let me solve the 26. So we haven't given that the step response, right? We haven't given the step response, we have to find the impulse response. I can use that differentiation formula, right? Given method 1, right? given step response is e raised to power minus 2t into u of t. Don't forget this u of t right now. Okay, so the impulse response, what will be the impulse response be? Impulse response will be ddt of step response, right? So just be careful while using this, because we have a unit step function here also. Okay, so what it will be? So if I differentiate the step, right, ddt of e raised to power minus 2t u of t, don't forget the unit step this time. So it will be uv, right, du dv, and v is outside, so u of t this time is outside, times the differentiation of this one, it is minus 2 e raised to power minus 2t and plus delta t. Okay, so this time differentiation of this one, right, this signal delta t, and this remains outside, it is to minus 2t. Now like delta t, right, it exists only for t equals to 0. So impulse only exists for t equals to 0, right? If impulse only exists for t equals to 0, then what will happen? For other time instants, it is 0. So delta t into e raised to power minus 2t is irrelevant before or after t. So only t equals to 0, I'll check the value and multiply with this delta t, right? So it becomes e raised to power 0 times delta of t, so it becomes delta t only. Okay, so now like what does our impulse response become? H of t, right? This is h of t only. It becomes delta t minus 2 e raised to power minus 2t u of t. So now if we integrate this back, right, just look at it. If you integrate this, you will get the step response. You will get the step response. Okay, so like that is for you to cross verify. Now let us do it from the method 2. Okay, the transfer function method basically. Okay, so how we'll do that? So we have been given that the step response, right? So we have the transfer function h of s, step response y of s. What is given? Y of t is given as e raised to power minus 2t u of t, and what is x of t for it? It is u of t only. Now do the Laplace, right? I should write here is simply h of t. Actually, do the Laplace. X of x becomes 1 over s. Laplace, it becomes h of s, and here also I do the Laplace, right? It becomes 1 by s plus 2. Okay, it becomes 1 by s plus 2. So if I divide y of s upon x of s, right, for a LTI system, we will find the transfer function, and if I do the Laplace inverse of that, I will find the impulse response, right? So s plus 2, s divided by s plus 2. So what is h of s? What I can write here is s plus 2 minus 2 divided by s plus 2. So it is 1 minus 2 divided by s plus 2. So it is like, now let me take the Laplace inverse, right? So Laplace inverse of 1 is delta of t, right? Delta of t minus 2 raised to power minus 2t. So this is h of t. Okay, this is our impulse response as from proof from earlier also. Okay, now like this lecture is 1 hour long, so what we will do is we have few questions like this one. This is actually 27 now. This has become 27 right now. Okay, we'll solve these questions in the, how many questions are we left with? Okay, too many questions, only 4 questions. Okay, I will solve, like take the screenshot of this. We'll solve this question in the, okay, let us solve this question anyways, even if this lecture has gone up, no worry. First, like watch this question, then you solve it for yourself, right? So let me write this as 27. So we have been given this transfer function. The unit impulse response of a unity feedback system control system is given like this. We have to find the open loop transfer function. Open loop transfer function we have to find, like in S domain, right? In S domain we have to find the open loop transfer function. This is a gate question, right? So this is a closed loop transfer function, and it is the unit impulse. So unit impulse, if I find the like the Laplace domain for this, we'll get the like simple the impulse response, right? So what I'll do, find the Laplace domain. So we'll find the CLTF. From CLTF we'll find the OLTF, as I mentioned in the formula, right? It is a unity gain, right? So unity gain, so that relation we will use, right? So we'll solve this pretty quickly. C of s equals to h of s equals to, taking the Laplace inverse. So Laplace inverse of minus t times e raised to minus t is, like, it is 1 by s square, then it is shifted by 1, then there is minus sign. So minus 1 by s plus 1 whole square, and this is 2 e raised to minus t, so plus 2 by s plus 1. Okay, this is one transfer function. Now we have to find the open loop transfer function. So what is the relation between OLTF and the closed loop transfer function? OLTF plus 1 plus OLTF equals to CLTF for unity feedback, right? For unity feedback. Okay, so what I can do here is simply again do the denominator difference, component of dividendo. So what I will do is like CLTF minus 1 by CLTF. So okay, let me further solve this actually. Let me make this common denominator. So this is 1 by s plus 1 whole square. So this becomes minus s minus 1 and s plus 1 whole square. So what does this become? Let me solve this actually. This becomes minus s minus 1 plus 2 s square plus 2 plus 4s. So what is getting cancelled here? Oh, sorry, I was doing something wrong. Okay, this will be like this will be minus 1 only, and this will be 2 into s plus 1, right? This will be s plus 1 whole square. Okay, so this will become 2s plus 1 divided by s plus 1 whole square, right? So this is this one. So what I will do now is the OLTF, right, will be 2s plus 1 divided by, like, I hope you are understanding how I am doing this. Simply component of dividendo, right? This is minus 1 actually. Okay, let me write this plus, yeah, like this one. Okay, so now if I do this, what I will get is 2s plus 1 divided by s square. Okay, so yeah, this is just a basic calculation. You can do it for yourself. This is another question. The unit step response of a system with transfer function g of s is given. Transfer function is given by which one of the following waveform? The transfer function is given for a system. Okay, we have to find the unit step response. Remember, this is a transfer function, right? This is the impulse domain given. We have to find the step response. So just finding the Laplace inverse of this won't be enough. So unit step is given. So what I will do, we have to find the unit response, right? So what I will do, we can do this, solve this using two methods. So first method is simply the transfer function is given, multiply that with the 1 by s, right? 1 by s, and get the output y of s, then do the Laplace inverse. Or other thing, apply initial value and final value theorem. So method 1 is initial value theorem or final value theorem. Okay, this is question 28 actually. Initial value theorem or final value theorem. So we haven't given the we have to find the unit step response, right? Step. So what we will do, x of s times h of s, so it is equals to x of s is 1 by s times h of s is this given, right, g of s, so it is 1 minus 2s divided by 1 plus s. Okay, so like what is this? So if I find this, right, if I find this, now this is given, right? What I will do, I will not solve this. What I will do, use initial value and final value theorem. So y of 0 equals to limit s tending to infinity s times this y of s, right? So what I am left with is limit s tending to infinity 1 minus 2s divided by 1 plus s. Okay, so it is basically equals to simply coefficient of the s, right, minus 2. Okay, and what will be y of infinity limit s tending to 0 is y of s equals to simply limit so if I put s equals to 0, what do I get? We're left with 1 only. So final value is settling to 1 only and initial value is 0 only. Okay, so final value is 1 only and initial value is not 0, it's minus 2. So minus 2 to 1 only, option A is going. So this will be our correct answer. Option A will be correct answer. So what is the method 2 for solving this question? So method 2 is just to find the inverse Laplace, right? So we know the step response. We know the step response, right, of in Laplace domain. It is 1 by s do the partial fraction method. Okay, sorry, do the partial fraction method. I'm solving this a bit quickly actually. So put s equals to 0. What do you get? This is 0, this is 0, 1 only, so we're left with 1 by s. Now put s equals to minus 1. Put s equals to minus 1, so this is minus 1, so minus 1, and this is minus 2 times minus 1, this is plus 2, 2 plus 1, 3, so 3 by 1, so this is plus 3 by 1 plus s, right? So okay, oh sorry, here we have minus 1 also, here we have minus 1 also, right? So okay, this is minus, that's why you shouldn't do hurry. Okay, so taking the Laplace inverse of this, what we get is 1 minus 3 e raised to power minus t, okay, into u of t, right? So this is the basically the step response, right? Step response. So if we see this graph, you will see that it is settling to 1 and starting from minus 2, following this curve only. Okay, so yeah, like this also you can find it out. Okay, so is there any other method for solving this question? So other method can be just simply finding the impulse response in time domain, then integrating it, right? So okay, I don't have space. Method 3, like wait up. Okay, h of t equals to 1 minus 2s divided by what was it, by 1 plus s. Now taking the Laplace inverse of this, okay, taking the Laplace inverse of this, what do you get? Let me first break this down, actually that will be easier for us to solve. So this is more difficult method, so don't have to try this if you don't like understand this 1 plus s, right? So if I want to take the Laplace inverse of this, so Laplace inverse of this one is easy only, it is e raised to power minus t u of t. But this one, right, it is difficult. What I will do is, 2 is outside constant only, so 2 will remain outside only. First I will find the Laplace transform of this part, Okay, 1 by 1 plus s, it is e raised to power minus t only. Then I will differentiate because s is multiplied. If s is multiplied, I will differentiate it, right? So it is e raised to power minus like differentiation of minus t e of t. Okay, so what do you get? What are we left with? E of t minus 2. There is another minus sign here. Okay, let me. Okay, so this is it. Okay, so what will be our impulse response become? So it will become, right, so there is here we have minus 2 multiplied, right? So it will become minus 2, like e raised to power minus t t at t equals to 0, this becomes 1. So we're only left with the delta signal, plus this becomes minus minus plus, and this is also plus. So e of t. Okay, so like what is this? We have to do the integration, right? So the step response, right? Generally step response we write like this s of t also. So we do the integration. So this is minus 2, integration of del of t is 1 only, plus 3 e raised to power minus tau d tau 0 to t. Okay, and e of t we are ignoring right now for now. So this is minus 2 plus this becomes basically 3 1 minus e raised to power minus t into e of t. This is also e of t, basically integration of impulses your step, right? So this becomes like 1 minus 3 e raised to power minus t into e of t. This is our step response, right? So using 3 methods you can solve this question, right? This is a very interesting question. Okay, so how many questions are left? So okay, like this is 29, I think this one was 28, 29. Now how much time has passed? Okay, we're almost past our threshold. So let me solve, like let me give you a few homework questions. Okay, this will be like assignment for you. Like this is also a gate question, right? So this is an assignment for you. You have to find in a feedback system, find the time constant for the closed loop system. This is an assignment for you. I will solve it in the notes and you have to understand it for yourself. Okay, and another question is this one is 30 only. 3 questions I am giving you homework, right? A first order low pass filter has following responses, right? So what you have to do is match those. Like how you will solve this? Like you will solve this using like that relation. The integration of one, right, is another. So integration of impulse response is step response. So whichever you are integrating and you are finding one, then you get the step response, and if you integrate again that, you get the ramp response. So if you integrate one signal 2 times and you are getting another signal, that means that the final signal is ramp and the initial signal was impulse. From there you will find impulse and ramp, and in between will be your step response. And this signal, right, what we'll do is like the time constant is tau only here for the open loop, right? Open loop tau. What you will do, you will find the closed loop transfer function using that formula g upon 1 plus gs. Okay, this is very easier actually. We can solve this now only. So like what you have to do is find the time constant of the closed loop system. So first you will find the CLDF g upon 1 plus gs. So I'm solving it anyways, so wasting time anyways, but I just thought like no, I can't give you, like maybe there will be some problem if I don't solve this. So this is 1 plus a by 1 plus s tau times what is h is beta. Okay, so a upon 1 plus s tau plus a beta. What I will do now is take common a beta, right? So this form is the time constant formatted. the coefficient of s is the time constant, right? So what I will do, take a beta common, so a upon, take 1 plus a beta common, a beta, so this is 1 s into tau upon 1 plus a beta, right? 1 plus a beta. So what is the time constant? What is the new time constant? Time constant of the closed system. So it is getting reduced. It is like what we are doing, right? Because time constant is getting reduced, the speed is getting increased. Okay, a beta. Okay, so yeah, it is getting reduced by 1 plus a beta. This is the like the open loop DC gain, whatever. Like if you see, this is the DC gain of this is a, this is beta, so yeah, a beta, like that. So this is another analog electronics concept. So from there you can understand. Here, like what I am observing is, if I integrate this, right? If I integrate this, I'll get this one. If I integrate this, I will get this one. So our R will be impulse, right? R will be impulse, and P will be step, and Q will be ramp. Okay, Q will be ramp. There was any option. Okay. Q will be ramp. So R is impulse, and what do you mean by impulse? Is X, right? So it is X, it is Y, and it is Z. So R is X. So R is X. Y is Q. No, Y is P. Y is P. Yeah, Y is P and Z is Q. Z is Q, right? So our option C matches. Okay, so that is the end of this whole chapter. So if I see any more questions or something, we may come up with more questions, but for this we are finished with chapter 1, that is the basics of control system. In next chapter we'll learn about the block diagram deduction techniques and the signal flow graph. Okay, thank you for watching.